Inter-process communication. Every day we open applications like a browser, a music player, a code editor, and many others. But have you ever wondered what actually happens when you click an application? At first, it is just a program. A program is simply code stored on a disk. It is not running, it is not doing any work, and it is simply a collection of instructions waiting to be executed. The moment you double-click the application, the operating system springs into action. The operating system loads the program into RAM, allocates memory, initializes resources, and creates something called a process. A process is simply a program in execution. Every process receives its own private address space. To know more about processes, check out process video here. Now, processes can be broadly classified into two types: independent processes and cooperating processes. An independent process does not share data or resources with any other process. It executes on its own and does not affect or get affected by other processes in the system. A cooperating process needs to share information with other processes. This cooperation helps achieve modularity, computational speedup, better performance, and resource sharing. However, processes are isolated and cannot directly access each other's memory. So how do they communicate? To solve this problem, operating systems provide inter-process communication, or IPC. IPC allows processes to exchange data and synchronize their activities safely while maintaining process isolation and system security. IPC can be broadly classified into two categories: shared memory and message passing. Shared memory. When Process 1 wants to communicate with Process 2, it requests the operating system, through system calls, to create a shared memory region. The kernel allocates a memory segment and maps the same region into the address spaces of both processes. Now both processes can directly read and write to the shared memory as if it were part of their own address space. Since data is exchanged directly through memory, the kernel is not involved in every read and write operation, making shared memory one of the fastest IPC mechanisms. However, because both processes can access the same memory simultaneously, synchronization mechanisms such as mutexes or semaphores are required to prevent race conditions and ensure data consistency. Shared memory is very fast, but it comes with a risk. Since multiple processes access the same memory region, a failure in one process can affect the others. A process may accidentally overwrite shared data, write invalid information, or crash while holding a lock. As a result, other processes may read corrupted, incomplete, or inconsistent data. Think of the OS as a house and processes as people in separate rooms. When they need to communicate, the OS creates a common room for both. That common room is called shared memory. The second IPC model is message passing. Instead of sharing memory, processes exchange messages through the operating system. The operating system creates a logical communication channel between two processes. Internally, the kernel manages buffers for storing and transferring messages. When Process 1 wants to send data, it sends to this kernel buffer. The kernel receives the message, stores it temporarily, and delivers it to Process 2. Think of it like a mailbox system. Process 1 writes a letter and puts it into a mailbox. The kernel acts as the postman, collecting the message and delivering it to Process 2. Since every message must pass through the kernel, message passing is generally slower than shared memory, but it provides better isolation and safety. Now, since processes cannot directly read from or write to kernel memory, the kernel provides APIs or system calls such as send and receive. Using these system calls, a process can send messages to the kernel-managed communication channel or receive messages from it. Since every message must pass through the kernel, involving system calls and data copying, message passing is generally slower than shared memory. However, it is safer because processes cannot accidentally overwrite each other's data. Same concept extends across computers. Process 2 of computer 2 sends data through a socket associated with a port number. The data travels through the network, reaches the destination computer, and is received by its network card of computer 1. The kernel then identifies the correct socket using the destination port number and delivers the message to the corresponding process. Check out video of file descriptor to get drunken.